First of all, thank you very much for inviting me to give this presentation. My name is Alex Glocer from NASA Goddard Space Flight Center, and the title of the presentation in the schedule is not the same as what I'm going to talk about because the organizers asked me instead to talk about an overview on modeling of ion escape from planets, and so that's mostly what I'm going to focus on. And so an outline more specifically of what I'm going to talk about is first I'll give a very brief overview of atmospheric escape and the role of ion outflow and what is ionospheric outflow. Then I'll do a follow the energy approach to see how energy inputs drive ion escape at Earth, looking at using modeling studies to look at the generation of ion upflow and also how that upflow converts into outflow. I'm then going to discuss ion escape at other planets and at exoplanets under extreme space weather conditions. And if there's time at the end, I'll briefly talk about the contribution of ions to hydrodynamic escape as well. So there's many different processes that go into atmospheric escape. There's genes escape, photochemical escape, hydrodynamic escape, sputtering, ion pickup, bulk escape. You know, I'm not going to talk about these in any detail because Guillaume gave a very nice overview of this in his presentation yesterday. But in this presentation, I'm going to focus on this blue box, which is ionospheric outflow, which you can sort of loosely define as the escape of ionized particles from the atmosphere through interactions with magnetic and electric fields. Now, ionospheric outflow isn't just one process, it's actually a whole zoo of processes. And if you look at the energy inputs, the high particle input and the electromagnetic energy input, those flow through multiple different processes in order to generate ion upflow and escape. Now, if this was a longer presentation, we could go into each one of these different boxes and talk about how they contribute, but you know, we only have 20 minutes. So instead, I'd like to focus on this very nice study from Strangeway 2005. And in this study, this is based on observations from the FAST satellite, looking at energy input in the form of Poynting flux and electric and soft electron precipitation above the cusp region. And in this study, there were multiple passes of the cusp region for a particular event, and these energy inputs were then correlated with ion outflow in the blue box. So energy input in and ion outflow out at 4,000 kilometers altitude. Now, the study also looked at correlations with these energy inputs with the wave heating that drives energization at high altitude, and then tried to infer causal mechanisms that bring the ions up from low altitudes to these higher altitudes where they can get further accelerated. And so in this presentation, I'm going to focus at least initially on this diagram, and we're going to walk through the different parts of this diagram and use some modeling in order to look at the efficiency of these different processes in driving upflow and outflow. And the scaling studies that I'm going to show are something that I'm working on with Lars Daldorf, and we're working on writing that up now. So hopefully that'll be available soon. So for the first part, I want to focus on this lower left part of the diagram where you have the Poynting flux driving Joule dissipation and then you know, increasing the ion scale height and driving ion upwelling. And so the idea here is that you have differential motion of the ions and the neutrals. So the motional electric field of the solar wind maps down to the ionosphere and drives a convection flow for the ions, but not the neutrals. And so you get a velocity difference between the ions in the neutrals. And that velocity difference shows up in the energy equation in the source term over here, where you get a frictional heating term that creates bulk heating of the ions. And so as this velocity difference increases, as shown here on the x-axis, it leads to large transient bulk upflows of the O+. And so this is O+ at an altitude of 1,200 kilometers. So you're seeing large flows of O+, going through the exobase transition region. So if you look at the flux, so you still have the velocity difference on the x-axis, and you have the flux of particles on the y-axis. You can see that, until you reach a certain amount of convection, you don't really get much change in the flux going through the exobase transition. Instead, you have to have a fairly sizable convection before you start to see that effect. And that effect is seen more strongly for the O+ than for the H+, although you see it in both particles populations. Now, if you move up to 4,000 kilometers, where the fast altitude, where fast was in this study I mentioned from Strangeway, you find that you have a different relationship. And part of that's because the O+ is very heavy, and not all of the O+ that's lofted through this heating mechanism will reach 4,000 kilometers, and some of it will fall back down. But you can see that you still get a sizable, for strong convection, you still get a sizable amount of O+ and H+ lofted to higher altitudes. Now, the second leg of this diagram that I want to talk about is the soft electron precipitation. And the soft electron precipitation is effective at driving outflow, mostly because it deposits its energy and ionization at the right altitude. So high energy electron precipitation penetrates very deeply into the atmosphere and produces ionization and heating low down, which is important for the formation of ionospheric conductance. But the soft electron precipitation, or in other words, the lower energy electron precipitation, deposits its energy and ionization at higher altitudes. And so this is a study from Su et al. Showing this. And so here, this is, higher energy, but still soft precipitation. And you see that the heating is less at high altitudes and more at low altitudes. And as you go to the lower energies, the peak of the heating moves to higher altitudes, and you get more energy deposition at higher altitudes. And so, just a second. Just 1 second. All right. And so how does ion upflow scale with soft electron precipitation? Well, we did some modeling of that. And in this case, what we did is we held the mean energy of the precipitation fixed at 100 electron volts. And then we scaled the electron energy flux, to increasing values from 0 to 5 ergs per centimeter squared per second. And we looked at the flux moving through the low altitude, exobase transition region. And what we find is that as you increase that electron energy flux, you're also going to increase the flux of particles moving through this region. And so basically more energy flux is giving you more ionization, it's giving you more heating, it's enhancing the ambipolar electric field. That's the electric field parallel to the magnetic field. And that's giving you more upflow. So, now you see how these two processes down in the lower part of the diagram drive ion upwelling. And so the last part of the diagram is talking about how ion upwelling gets converted into ion outflow. And so the process here is with wave particle interactions. And it's important to remember that the heavy ions like O plus require 10 electron volts to overcome gravity. And so they don't quite get enough energy to reach escape velocities from these lower altitude processes. On the other hand, they can get more energy along the way. And so at the high altitudes, there's this wave heating process. And so the idea is that you have some wave power available at high altitudes. This can come in a number of different forms. There's electrostatic ion cyclotron waves, there's lower hybrid waves, broadband electromagnetic low frequency waves, dispersive Alfvén waves. There's a whole host of different plasma waves available from different processes. But the idea is that a particle that's gyrating around a field, around the magnetic field that encounters these waves will interact with them. And either they'll interact resonantly, along the gyration, as in the case with like the lower hybrid or the BB-ELF waves, or in a finite Larmor radius scattering type of interaction, such as with the dispersive Alfvén waves. But regardless of the specific mode of interaction with the waves, the net effect is that you get a transverse heating, so a heating perpendicular to the magnetic field. Now that transverse heating gives you a lot of, gets converted into organized parallel motion via the mirror force. So you get this random perpendicular motion converted into organized parallel motion. And so this is the momentum equation for a particle gyrating around the field. And this term is the mirror force term that's converting this perpendicular motion to parallel flow. And this gives you the formation of what's called an ion conic distribution. So this is the velocity space distribution function, which is very non-Maxwellian for these heated ion conics that are frequently observed above the Earth's cusps in auroral regions. And so this is a simulation of how this process works. So this is from one of my papers in 2018. And so this is a field line above the Earth's cusp. And if you look at low altitudes, the velocity space distribution is a Maxwellian. And as it gets heated by the waves, the perpendicular heating becomes stronger and stronger. And eventually you see the formation of this ion conic distribution in velocity space. And you can see the effect on the moments of the ion outflow. These are altitude profiles of density and velocity. And if you just focus on the O+, which are these dashed lines, the red is with no wave heating and the black is with the wave heating. And you see that with the wave heating, the number density at high altitudes goes up significantly, and the velocity goes from relatively low flow or stagnant to around 13, 14 kilometers per second flowing of O+ flowing out of the top of the simulation. And so you really can pick up a lot of energy this way. And you can look at how this scales with the wave. So if you put just like with the other processes, if you put the strength of the wave, so this is the power spectral density. In this case, we're using the BB-ELF waves, the ion cyclotron resonant heating mechanism. And you look at the wave strength on the x-axis and the flux on the y-axis, you can see that once you hit a critical strength of the waves, then the flux starts to grow, the O+ flux in particular starts to grow with the power law distribution until it reaches some limit, whereas you put more energy in, you just can't pull any more out of the ionosphere. You reach a limiting flux. And the lower boundary is basically set by a polar wind type process. But of course, this is with no precipitation. If you also had precipitation, when we're lofting up particles from lower down, having this low altitude ion upwelling, that will change these scaling laws. And so here, this is the result when you include soft electron precipitation. And you see that the power law changes, and also the minimum flux changes, as does the maximum flux. and the relation of how much is O plus and how much is H plus will change. And so you have multiple things going on simultaneously in this two-step process of low altitude upwelling and high altitude acceleration, really work in tandem to give you what you see. And it's not just, the particle precipitation and Joule heating, the solar ionizing flux is also important. So this is showing you the result for a solar minimum case, so a reduced solar ionizing flux. And you get, as you can see, different power law relationships, different limiting fluxes, etc. So I don't want to spend too much more time on this. I'll just say that, from this walkthrough of the Strangeway 2005 diagram, you can see, thank you. You can see that the low altitude heating can be very effective in lofting ions up through the exobase transition. The high altitude wave heating can then heat those heavier ions to help them overcome the escape velocity. And that when you combine these different things together, you can change the response. And now there's a number of caveats in what I showed you, but I'd say a major thing is that there exists a number of large unknowns in terms of predicting the key energy inputs from first principles models. In particular, the wave power is very difficult to predict from first principles models. So there's a lot of work that needs to be done still. Now, I'd like to talk very briefly about ion escape from planets and exoplanets. And so I just say just one example is that, ion outflow is not just a process for Earth, but it's been seen at basically all celestial, bodies, in our solar system. And one example is Jupiter. And I'm not going to spend a lot of time on this, but just to point out that, there's observations of H3 plus in Jupiter's magnetosphere. And, in Earth's magnetosphere, when you see O plus, it can only come from the ionosphere. So when you see it out in the magnetosphere, it's very clear indicator of an ionospheric source of plasma. And at Jupiter, H3 plus is very similar. When you see H3 plus in the magnetosphere, it's indicative of an ionospheric supply of plasma. But there's also now with Juno, there's direct observations of ion conics from these wave particle interactions, from this paper from George Clark. And I won't spend too much time on this, but just pointing out that these processes are universal. It's not just a process for Earth. Going to one of the main topics of this workshop is how does the size of the magnetic field impact the ion outflow? This is just showing a plot of the stellar wind coupling function. So this is the VBZ of the solar wind, which is, a rough indicator of the coupling to the magnetosphere. And on the y-axis, I'm showing the cross-polar cap potential, which I'm using as a proxy for the energy transfer to the atmosphere. And you can see that, as you increase the solar wind driving for an Earth-sized dipole, it will go up and up and up until eventually it will start to bend over. And if I continued this curve, it would saturate. And if I multiply that magnetic field by 4, that whole curve shifts upward. I get more energy transfer to the atmosphere. But again, it will saturate at some point. And so this cross-polar cap potential correlates roughly with the Joule heating that you'll see. So that will affect the low altitude upwelling and ion outflow. But it's not so easy just to say that you increase the magnetic field and increase the stellar wind, you'll drive more energy input. You have to consider the saturation effects as well. So I'm just going to talk very briefly in the last minute about what are the implications for exoplanets. And as you heard in a number of talks yesterday, there are a lot of close-in exoplanets that experience very strong stellar winds and very strong radiation. And when you have those strong stellar winds, you're going to get more Joule heating. And so this is a paper from Offer Cohen a few years ago comparing the expected Joule heating for a planet around a close-in exoplanet compared to Earth with the CME. And you can see that you get very strong Joule heating, which may imply strong upflow. But you can also get enhanced ion outflow with stronger EUV and XUV input. And so this is a paper that was led by Vladimir Arpetian showing, the outflow calculation for different XUV inputs, and also the size of the polar cap increasing for the stronger stellar wind inputs. This is using the Batsar-Russ MHD code. And what you find is that these conditions give you more outflow, and you can get actually really large ion outflow loss integrated over the polar cap under these extreme conditions. Catherine Garcia-Sage showed something very similar for Proxima Cen-B, using similar types of simulations. And what she found is that if you look at the mass loss time and compare that to the age of Proxima Cen-B, it's possible through just ion loss from enhanced EUV and XUV input that you could evacuate all of the atmosphere from this process when you have very extreme energy inputs. And now I think I'm done in terms of time. So I just say that ion outflow can also contribute to hydrodynamic escape. And I'm not going to spend any time on this since I'm really at my limit. I'll just point out that if you look at the ion fraction, for strong EUV, XUV inputs, that the ion fraction of the hydrodynamic escape can grow significantly. And so some of that hydrodynamic escape is not just neutral escape, but can be ion escape, in which case we should start considering how ion outflow processes like ambipolar field and wave heating and whatnot can start to contribute and modify the hydrodynamic escape. So I think that's it. I think I'll leave my summary up here so I don't put us behind schedule from the beginning, and just take any questions. And thank you.
Thank you, Alex. So we are now in open discussion. So if you have a question, please raise your hand or use chat or Slack, please. Lim, please.
So we've been doing some the strange way analysis, but including composition data, so separating protons from oxygen. Kai Zhao is presenting a poster of some of these results in this afternoon. But one striking result that we found is that on the night side, the proton outflow correlates almost exclusively with the soft electron precipitation, whereas the oxygen correlates with everything, the pointing flux, and as well as the precipitation and so on. Would that be your expectation? It almost looked like that from some of your plots.
It's interesting you say that, and I think yes, it does make sense to me, and the reason is that if you look at the H plus, without any precipitation, the polar wind flow is very, very close to the limiting flux. So putting in more wave power doesn't actually accelerate any more H plus out. You give it more velocity, but you're already at your limiting flux or very close to it. But when you include the soft electron precipitation, now you can change what those limits are. And so you give yourself more room to work with. And so I know the paper you're talking about. I think it's a really great paper. But I think that might be part of the reason why you see the correlation with the electron precipitation for H plus, but not with the wave power.
Okay, thank you.
I'm happy to talk with you more about it offline if you like.
Sure, and please stop by the poster in the afternoon or whenever.
Yeah, I definitely will.
There are some questions on the chat. So first one is the ion upflows are different from the ion outflows as you talked. How you can convert the Joule heating to ion escape rate? Is there any way to estimate additional wave heating?
Yeah, it's an interesting question. So the Joule heating will give you upflow, and it'll give you a transient upflow, but you need some additional energy to really convert that to an escape. And so I think that's one of the hard things is that generating this upflow is not quite enough by itself, but it can enhance the ion outflow. And so one of the things that we tried to do with the modeling is to say, how much upflow can you get by itself? And then under different assumptions of the wave heating, how much of that will get converted to outflow. But it's hard to do it in general. You really have to just consider specific cases.
Okay, so there are two more questions, but it's almost time to move on next. So please contact us in Slack. So thank you, Alex.
Okay. Thank you very much.